Firstly, privileged to be talking at CogX. It's grand. And thank you also, everyone, for staying with me and coming to talk. I know it's very hot in here. I can see a lot of fans going. But yeah, thanks for kind of persevering. I'm going to talk to you a little bit about information highways and navigating the network. So that may not be entirely clear yet, but I hope it, over the course of the talk, will become a bit more apparent. So let's get started. So the overview of what I'm going to talk about is, firstly, I'm going to very quickly kind of review CNNs and their successes. So quick show of hands, who kind of understands what a CNN is, what it does, kind of how it works? OK, that's pretty good, nearly everyone, grand. And then after that, we're going to talk about robustness, adversarial examples, barriers to further adoption, and kind of maybe the kind of drawbacks on or how we get CNNs out into more kind of high-risk applications. I then want to talk a little bit about the kind of importance and role of activation pathways. Then present with you the deep convolutional sparse coding framework. Anyone heard of kind of compressed sensing sparse coding here? Oh, cool. I did not expect anyone to have done it. Grand. And then I suppose the big main result is going to be a probabilistic bound on the recovery of activation pathways by the forward pass. And then finally, we're going to discuss some limitations and then have a little kind of look to the future and what we can do next. And in general, I want to try and keep the kind of level of the talk quite high level, kind of more focusing on intuition, motivation, than the kind of nitty-gritty technical detail. So hopefully it'll be fun. So without further ado, a convolutional neural network. So really all it is, I suppose, a normal neural network, but with a particular local enforced kind of pattern of connections. So unlike the kind of example on the right-hand side, which is densely connected, our nodes on a given layer are only connected to a few nodes in the previous layer. And that brings some benefits. So the first one maybe we can identify is the fact that we're kind of focusing maybe on more local features now in an image or in a piece of data rather than the whole global picture. And that, I suppose, is nice because we can pick out local features instead of just global ones. But also, it provides us a degree of translation invariance, which is, of course, beneficial when you're dealing with data that's kind of got all types of nuisance variables in it. The second thing is that it's not only sparsely connected, but we typically share weights. And what I mean by share weights is that we essentially, in some sense, have the same filter can be applied to many parts of the image. And so we essentially have far fewer parameters than we would maybe in a global, kind of densely connected network. And this means computationally it's easy to train. And also we have a lower risk of overfitting. So what is all the fuss about? Why do we care about CNNs? This slide is probably going to be pretty familiar to a lot of you. First of all, they do a pretty good job at image classification. So the ImageNet kind of competition, it's been running for quite a few years now. We're getting to the point where these systems can actually beat human beings. And CNNs really have been the driving force behind that. If you can see to the left of that, so kind of pre-2012 and AlexNet, we were up around kind of 25% misclassification on ImageNet with these kind of systems. And then when we brought CNNs in, we can see we've gone down now to around 3.1 in 2016, which supposedly beats the kind of human benchmark. And although that's very cool, we probably shouldn't get too carried away. There's quite a few examples where maybe the human being just doesn't know a particular breed of dog, for instance, and hasn't had the kind of luxury of looking at 3 million pictures of different types of dog breed. But it's still a pretty impressive kind of show of force nonetheless. And so that's grand, and we've taken ImageNet, and now we're thinking about the kind of wider potential applications. We're getting very excited, as we should do. So we're talking about things like self-driving cars, even drug discovery, natural language processing, and robotics. So I think as this kind of whole venue and festival is around, it's a very kind of exciting time for AI. But I think there is, I suppose, room for potential, not potential like cynicism or pessimism, but we need to be careful not to get kind of too carried away too quickly. So if you maybe have seen some of the talks earlier, you might have seen this diagram on the left already. But this is really an adversarial example, which I suppose in some sense highlights one of the issues with neural networks. And the fact is we've got on the left-hand side a panda, and then we adjust the pixels very slightly by adding a mask, so kind of changing the pixel value, just a very tiny bit. On the right-hand side, we see still it's a panda, looks exactly like the image on the left, but the neural network, the CNN, thinks it's a gibbon. And moreover, it kind of thinks it's a given with far more certainty than it thought the left-hand one was a panda. So it's kind of clear that these systems aren't quite working in the same way that we think they do. They don't have that level and that kind of contextual awareness that maybe a human being has. And I think most people would agree that's kind of a cause of concern if you want to start using it in something like a self-driving car or an aviation or anything where there are higher kind of risks at stake rather than just the kind of opportunity loss as you might get on a piece of advertising. So I'm going to argue that to understand the failure modes of neural networks, we need to really just, I suppose, understand a bit better how they work. And there'll be many ways you can kind of think about how to break the kind of problem space and the kind of theory space of neural networks kind of up into. But I've kind of highlighted kind of 4 regions. So firstly, approximation. That's about the forward pass algorithm. What functions can it approximate? How does it map input data to output data? That might be, for instance, labels. And there's been a lot of work, and some of that work goes right back to the 1990s, and is really interesting and some very powerful results. The second one is optimization. So I tell you that we can, I suppose, approximate nearly any function or any function that has certain properties with a neural network, but how do I actually configure my parameters of my model so that I actually approximate that function? How do I find that function? The third one then I would argue is generalization. So that's around, so fine, I've trained my network. It does fantastically on my trained data. Maybe it even does well on my test data. How do I know? How can I be sure that it will do well on new examples? How can I be sure that I can rely and trust it in a high-risk application? And finally, stability, which really kind of comes back to this kind of adversarial example point of view. How can we guarantee or determine that the neural network will behave as we want it to do? And this is something that is a bit different to a lot of kind of classic kind of control theory, for instance, and even things like systems verification in computer science, where we're able to tell within reason, or at least bound probabilistically, how our kind of systems will operate. So my goal then, and I suppose our goal in all of us, is to really understand the forward pass algorithm, which I would argue is the workhorse of a convolutional neural network, and the way in which kind of information and knowledge is stored and organized in a CNN. So a kind of bit of a kind of toy example to get kind of everyone in the kind of frame of thinking in the right mind. So the role of the forward pass algorithm is to map my data, in whatever form it is, into a new space, which I'm going to call the task space or encoding space, in a way that it makes it kind of well suited for a task. So on the left-hand side, you'll see we've got a kind of a set of data. This data lives in a 2-dimensional space of real numbers, so scalars. So with each data point, I associate 2 numbers. And I want to classify them. And there's 2 classes. I want a simple rule for my computer to be able to determine and distinguish between those 2 classes. Now, if I just wanted to draw a line and say, right, if the number is bigger than this, bigger than that, it's this class, and if not, the other one, I cannot really do that. I can't draw a line on my left-hand plot and say, right, here's a simple rule, go get them, computer. But what I can do is I can compute a feature, a very simple feature, which is basically the distance of my data point to the origin. And you can see by the form of the data, using this, I should very easily actually be able to classify the data points on one side or another. And this idea of a feature is going to be a kind of a recurring point, and is a key kind of point for kind of machine learning and what really the forward pass is all about. So what actually happens when we train a neural network? So there's a lot of kind of ways this is described, and I argue kind of one of the main kind of ones that's taken kind of hold in at least maybe the 5 years, this idea of kind of hierarchy of features or hierarchy of representations. So this is an image from Andrew Ng. It's quite a, or Andrew Ng, sorry. It's quite a nice one. So it shows basically that in the lower levels of my neural network, I'm essentially trying to identify quite simple features. So in the same way that maybe I constructed a rule that was to calculate the radius of my data point, in some sense, on the kind of other slide, here I'm saying, right, I'm going to compute some object and then compare it with my new data points. In some sense, this feature is going to be a template that I'm going to try and find in, for example, an image. And you can see early on in my network, the very first things it looks for are images. And the idea is you build up a hierarchy of representations by then having slightly larger local features. So, for example, noses, ears, eyes. And these are made up of a combination of edges. And then finally, I can construct and, in some sense, combine those kind of mid-level features to form global features and large-scale features like faces. And that's kind of the real key kind of intuition, at least that's what most people will tell you is how kind of, I think, like neural networks work. So yeah. So before we go any further then, I want to start now introducing the idea of this activation pathway. So if we think about a single node and what a single node does in light of the previous slide, what a single node really does in terms of how you can think about it is, I suppose, match part of the data with a template. So we can think of this node as having an encoding of a particular feature, like an edge, or maybe a nose, or maybe a face, in its weights. And then you look at your image or your piece of data, and you try and see if that feature is present. And if that feature in some sense is present, then my node is going to activate. It's going to be non-zero. And this is a particular, you can use different activation functions, but for the sake of this talk, we're mostly going to focus on the ReLU, which is a particular activation function that I think is probably the most common one used in practical machine learning today. So yeah, I mean, that's kind of really what it's about. And I mean, if anyone's still struggling with the intuition there, you can imagine I've got a 6, for example. I'm using MNIST. My image is a set of pixels. Maybe it's binary. The parts where it is 6, it's valued 1. The parts off the 6 are valued 0. If my template also looked a bit like a 6, and I multiplied each pixel value together and then added them all up, in some sense, that would give me a high activation. Whereas if my template looked more like, I don't know, a 1 that was off to the side, maybe there wouldn't be very much overlap. And therefore, this node wouldn't activate. And in that sense, I hope we can see that kind of nodes really pick out features and indicate that a feature is present. And therefore are critical, really, in viewing how the neural network interprets data in terms of its own internal set of representations. So now I'm going to kind of say, well, what about we look at the neural network as a whole and consider not just kind of the activation of one node, but the pattern of nodes across the network. So in this example, we've got like a cute little puppy and a cat. And we can see that they've actually activated a different sequence of nodes as we kind of go through the network. So the kind of dog image, maybe, we can say, well, he's got a particular collection of edges. The cat has a slightly different collection of edges. Then in the middle sections, maybe the dog like hits up and says, right, there's a nose and some floppy ears and a pair of paws. And the cat, we say, well, we've got some pointy ears and some whiskers. And at the end of the day, we combine those then higher-level features and say cat or dog. And the key thing, I suppose, then, is really saying that these activation pathways, I suppose, allow us to understand how the neural network interprets the data points it has in terms of the examples and templates it's seen. How does it correlate what it's past learned with the new data? So this point is where we, I suppose, start to introduce the work we've been doing. And it's built on some work from some guys out of the Technion in Israel. And the idea, really, I suppose, is to interpret the forward path of the neural network as solving a sequence of sparse coding problems. Let's not worry too much about what that is for the moment. I'm hoping I can kind of explain it intuitively. But let's play a game. And let's say instead of having an image of a dog, I have a representation of the dog in the encoding space. So this is some abstract representation, probably of 1s and 0s, which maybe are things, for example, like ears, paws, nose. Then what I'm going to do is I'm going to almost work kind of the reverse way through my network. I'm going to try and build up an image of my dog from my templates by adding them together. So in some sense, I can see my kind of encoding space gives kind of commands and instructions on how to build my picture of a dog. And so this kind of reverse pass is in some sense rendering an image of a dog from the neural network's understanding of what a dog is, from its kind of latent representations. Then what I'm going to do is I'm going to say, well, it's unlikely that all the information in all my training data has been captured by the neural network. It's also unlikely that this is, well, for one thing, it's a new image of a dog. So there's going to be some information in that dog that isn't captured by my latent representation. And let's face it, it shouldn't be. We don't want our neural network to simply memorize what data is. Part of learning is about throwing away the unimportant stuff for the task at hand and holding on to the stuff that really matters. So at the end, I've got this thing that I'm calling x hat naught. And don't worry about too much kind of what that is for the moment. But let's kind of envisage that it's a dog that's in some sense close to our view of what the neural network's view of what a dog is. And my game I want to play is I want to say, well, when does the forward pass algorithm, as it is, recover the activation path, i.e. the sequence of nodes that are activated at every layer, and when does it not? In some sense, we can view this as kind of, I suppose, analyzing the failure modes of this recovery. And we'll get a bit more into interpreting what the kind of real nitty-gritty of that means kind of towards the end. But kind of if we just kind of roll with that for the moment. Note that we're also saying here that we are assuming we have a trained neural network. So I'm in a situation where I've trained my network, and we are now just analyzing that forward pass. And also the fact that, being slightly cheeky, I'm no longer using ReLUs. I'm using something called a hard thresholding function, which is very common in sparse coding and compressed sensing. It's really very similar. It's just a slightly different form of kind of activation. So here is the bound that we've kind of come up with. I don't expect you to kind of read it and intuitively get it, but this is kind of the result that we're saying that you can be proved. And essentially what we're saying here is that I can bound the probability to the activation path is recovered. I can provide an upper bound on the failure and therefore a lower bound on success. And the things that this relies on, I suppose, are firstly, we have to say the kind of distance of our image that we're processing from our kind of internal representations of the data can't be too far. And that's kind of captured in this kind of VL term. And so it's in a kind of energy term saying, well, the kind of distance of our image to our model can't be too far, otherwise we'll run into problems. The second thing is I'm implying or kind of asserting some sparsity constraints on the data that I have. I'm saying at every layer, I can't activate too many nodes. In other words, my signal can't be too complex with regards to my kind of underlying neural network. But yeah, so we can do this, and this is all very fun and very exciting. I suppose we should, though, discuss some of the limitations of this work. So first of all, you'll note that it's a sufficient condition and not necessary. So that means if, for example, my data point doesn't satisfy the conditions that I've stated, it doesn't mean that it won't be recovered. It just means I can't really say very much about it. Secondly, for the bound to be non-trivial, those sparsity conditions and also the kind of noise condition that I kind of stated and alluded to earlier have to be satisfied as well. So it can't be, I suppose, it is not super robust to noise, this piece of analysis. And lastly, what I think is probably the most poignant point is that exact recovery of this reverse activation pathway may not be entirely necessary for kind of understanding why CNNs work. And why I say that is because really, we don't necessarily need our neural network to be in some sense invertible, right? If I take a latent representation of a dog or a cat in my encoding space, it's not really necessary for me that forward pass be invertible. I don't need to recreate the exact kind of dog that I had in the first place. In some sense, that's kind of going back to the idea again that we're not throwing away the unimportant information here. In some sense, we want a kind of many-to-one function, not a kind of one-to-one and onto function. Okay, so kind of how do we take that kind of result and kind of go a step further? So I'd say then our future goal then is instead of understanding maybe how a single data point traverses this network and navigates the network along its activation path, we want to really understand the information highways in the network. How the network organizes data and routes members of different classes through its structure, and whether there's any gains we can get from understanding that in a bit more detail. So for example, to the adversarial point, really what that's about is by saying that our data points exist in some very high dimensional space. There's a very small gap, very small distance that we can jump across, and suddenly we'll be in a completely new class. And that maybe suggests that perhaps the way our data is being mapped into our kind of encoding space could potentially be formed in a slightly different way. So perhaps we could separate classes in a slightly kind of neater or better manner, or perhaps we just need to make them kind of connected in some sense. So to kind of summarize kind of what we've said in the talk, so I think hopefully we've kind of motivated why a deeper understanding of CNNs is kind of required to better facilitate their deployment in higher risk applications. And I think that's really where the kind of like future part of neural networks can be and where the kind of really excitement is. So it's not maybe necessarily just in advertising, but yeah, can we get robots and self-driving cars kind of working using these tools and safely rely on them? The second then, and kind of the second point that I think I hopefully have conveyed is perhaps the importance of this idea of the activation pathway and what that means in terms of interpreting what the CNN is doing. Finally, I introduced what we call the DCSC, the Deep Convolutional Sparse Coding Model, and the reverse activation pathway as a way of analyzing the kind of efficacy of the forward pass and what it's doing. And then I think we kind of then were able to show a bound and then also discuss kind of future work, which hopefully kind of at least sounds exciting and kind of interesting. So that's kind of my talk. Thanks very much for listening. Yeah.